Pearson's correlation is a statistical measure of the linear relationship between two continuous variables and is basically denoted by a small letter r. In SPSS, Pearson's correlation analysis is a straightforward bivariate procedure that produces the strength and direction of a linear relationship between continuous variables drawn from a population that is normally distributed. So when you perform Pearson's correlation analysis, the main result outputs include 1. The strength of the correlation given by the magnitude of the coefficient. 2. The direction of the correlation given by the positive and negative indices attached to the coefficient. And 3. The probability that indicates a significant or insignificant relationship given by the p-value, which is needed to reject or accept the established null hypothesis. But before I demonstrate the SPSS procedure and give detailed interpretation of the results output, let's take a look at the dataset, the parametric conditions or assumptions that the data must satisfy in order to be tenable for the analysis, and the hypothesis that needs to be tested. My name is Titocan, and this is Titocan Solutions, a YouTube channel for improving the knowledge of how to do things. To perform Pearson's correlation analysis, you must have a dataset like this, consisting of two continuous sample variables, or a dataset like this, consisting of several continuous sample variables. The sample data can be any type of parameters, provided they are not nominal or ordinal variables. Whatever number of continuous variables you have, SPSS will be able to conduct a pairwise correlation analysis on them and produce the results as appropriate. As you can see, this dataset consists of 4 sample variables. From this set of data, you can perform the Pearson's correlation on only 2 sample variables, or perform the Pearson's correlation on all 4 variables, just as we are going to do later. Though Pearson's correlation specifically measures the linear relationship between 2 continuous variables, SPSS has the capability to process the Pearson's correlation analysis for more than 2 continuous variables at a time and still produce the linear relationship between the 2 variables in terms of the magnitude of the strength of the coefficient and direction in an output table called correlation matrix. However, it is important to know that this dataset is simulated to suit this demonstration, and as a result has been tested for the parametric assumptions and has been found tenable for the analysis as the data satisfied all the assumptions. If, however, you want me to demonstrate how to test for the assumptions, please kindly let me know in the comment section, and I shall develop a video and publish it for you to see. Usually, for Pearson's correlation, the units of the variables don't necessarily have to be homogeneous. What is important is that the variables must be continuous variables measured at interval or ratio level. For your data to be tenable for Pearson's correlation analysis, there are a few assumptions that your dataset must satisfy. The assumptions are: 1. Your 2 variables should be measured on a continuous scale, that is, they are measured at the interval or ratio level. 2. There should be a linear relationship between the variables. 3. There should be independence of observations. This means that the 2 observations for one case should be independent of the 2 observations for any other case. 4. There should be no significant outliers. This is because outliers can lead to misleading results, and Pearson's correlation coefficient is sensitive to outliers. And 5. Your variables should be approximately normally distributed. That is, your data should have bivariate normality in order to assess the statistical significance of the Pearson's correlation. Now, the hypothesis. A correlation coefficient is usually calculated with sample data taken from the population, and in statistics, we always intend to test a hypothesis about the population. So for this correlation analysis, we want to check whether the correlation coefficient in the sample is statistically significantly different from 0. So we can state the hypothesis as follows. The null hypothesis states that the correlation coefficient does not differ significantly from 0. That is, there is no linear relationship between sample variables, while the alternate hypothesis states that the correlation coefficient differs significantly from 0. That is, there is a linear relationship between sample variables. The statistical information carried by these hypotheses is enormous, and we shall divulge them when we interpret the result outputs of the analysis. But be informed that when you are testing hypotheses, the intention is to reject the null hypothesis, because the null hypothesis always projects the bad part of the expectation, just as the name implies, null. So our intention will be to hopefully have p-values less than 0.05 in order to have sufficient evidence to reject the null hypothesis. Now, without further ado, let's perform the analysis. Go to the menu bar and click on Analyze. From the sub-menu, put your cursor on Correlate. And from the drop-down options, click on Bivariate to open the Bivariate correlation dialog box. Your variables are in the box on the left. As you can see, I have sample 1, sample 2, sample 3, and sample 4 in the box. If you are interested in performing Pearson's correlation for only 2 sample variables, you can select the 2 variables only and move them to the variables box on the right. But for this video, I want to create a correlation matrix, so I will be using all the 4 sample variables. So I will click on sample 1, hold down the Shift key on my keyboard, and click on the last variable, sample 4, to select all the variables. Then, click the transfer arrow key to move them to the variables box on the right. Now click on the Options button to open the Bivariate Correlation Options dialog box. In this dialog box, check the box for means and standard deviation. And this selection will produce the descriptive statistics of the variables, such as the mean, the standard deviation, and the number of observations per sample or number of cases. If there are missing data or missing values in your dataset, your data may not be correctly analyzed and your results output might be wrong. So you will have to choose either the exclude case pairwise or the exclude case listwise to fix the missing data or missing values in your dataset before running the analysis. Please note that if there are missing values in your dataset and you choose either the pairwise or the listwise setting to fix the missing values, such a choice will not affect your correlation computation if you have only 2 variables to consider for the correlation analysis. But any of the choice will have significant impact on your results if you are entering more than 2 variables for the analysis. So you must ensure that your data doesn't have missing values or missing data before you run the Pearson's correlation analysis. But since my data doesn't have any missing value, I will just ignore the missing value section and go ahead to click the Continue button to close this dialog box. In the correlation coefficient section of this dialog box, there are 3 options. That is the Pearson's correlation, Kendall's-Taubbe correlation, and the Spearman correlation. But since in this video we are performing Pearson's correlation, I will just check the box for Pearson's correlation. However, this box has already been checked by default. For a test of significance, the default selection here is two-tailed, and that is what you should select, since Pearson's correlation measures the strength and direction of the relationship between 2 sample variables from a population, which lies between -1 and +1 at a significance level of 0.05. Two-tailed test of significance will be able to test the coefficient and the direction of the correlation. But if you select a one-tailed test of significance, it means you won't be considering the direction of operation of the correlation. Now, leave the checked box for flag significant correlation unchanged so that the coefficients that are significant at 0.05 or at 0.01 will be indicated with asterisk mark as superscript to the coefficients and also defined under the correlation table. Now we have completed the Pearson's correlation analysis settings and there is nothing more to do. So click OK to run the analysis and produce the Pearson's correlation results in the output window. As you can see, the results have been produced in 2 different tables. The first table is the descriptive statistics table and the second table is the correlation table. The descriptive statistics table highlights the mean, the standard deviation, and the sample sizes of the variables. As you can see, all the sample variables have equal sample sizes of 20 each, which indicates that there were no missing values in the dataset. You can take the results of the mean and standard deviation and put them in the body of your work because such information is very important. Now, let's proceed to the correlation table. But before I discuss the results in this table, there are two basic things I want you to put into consideration. One, the index to interpret the correlation coefficients, and two, the index to interpret the p-values. Now, this is the index to interpret the correlation coefficients. As regards, if the correlation coefficient lies between 0.0 and less than 0.10, it means there is no correlation between the two sample variables. If the correlation coefficient lies between 0.10 and less than 0.30, it means the correlation between the two sample variables is low. If the correlation coefficient lies between 0.30 and less than 0.50, it means there is a median correlation between the two sample variables. If the correlation coefficient lies between 0.50 and less than 0.70, it means the correlation between the two sample variables is strong or high. If the correlation coefficient lies between 0.70 and less than 1.0, it means the correlation between the two sample variables is very strong or very high. If the correlation coefficient is exactly 1.0, it means there is a perfect correlation between the two sample variables. These are also true and same if the coefficients are negatives. Now, this is the index to interpret the p-values. If the p-value is less than 0.05, reject the null hypothesis because there is a correlation between the sample variables. But if the p-value is greater than 0.05, you will have no sufficient evidence to reject the null hypothesis because there is no correlation between the sample variables. Now that we are guided on how to interpret the coefficients and the p-values, let's now pay attention to the correlation table. When a variable correlates with itself, the correlation coefficient is 1, and this value is described in the index table as a perfect correlation. The p-value is usually not given for a coefficient that is equal to 1 because the correlation is perfect. As you can see from this table, there is a perfect correlation between a sample variable and itself along the leading diagonal. That is, the Pearson's correlation of sample 1 with sample 1 is 1. The Pearson's correlation of sample 2 with sample 2 is 1. The Pearson's correlation of sample 3 with sample 3 is 1. And the Pearson's correlation of sample 4 with sample 4 is 1. This diagonal separates this table into two similar triangles. So the coefficients above the leading diagonal are exactly the same coefficients below the leading diagonal. But to avoid confusion, I have restructured the table by removing the coefficients above the leading diagonal line and presented it like this, the way you are expected to present the table in your work. Like this, the correlation table is clean, clear, and usable. Now, as you can see, the correlation coefficient between sample 2 and sample 1 is 0.018 and is a positive value. But if you look at the index table, this coefficient falls between 0.0 and less than 0.10, and this indicates that there is no linear relationship between the two samples. Since the coefficient is positive and there is no linear correlation between the two variables, there will be nothing to talk about the positive sign, which is supposed to indicate the direction of the correlation. So the graph will be the type that projects from the y-axis and parallel to the x-axis. Accordingly, the p-value is 0.941, which is greater than 0.05. From the index of p-value table, this means that we do not have sufficient evidence to reject the null hypothesis because the correlation coefficient does not differ significantly from 0, meaning there is no linear relationship between the two sample variables. Now, the correlation coefficient between sample 3 and sample 1 is 0.894 and is a positive value. Again, if you look at the index table, this coefficient falls between 0.70 and less than 1.0, and this indicates that there is a very strong linear correlation between the two samples. Since the coefficient is positive and there is a linear correlation between the variables, it means that as sample 3 increases up the scale, sample 1 simultaneously increases up the scale. So the graph will be the type that projects from the origin of the x and y axis in an increasing pattern. The double asterisk mark standing as superscript to the coefficient showed that the correlation is significant even at 0.01. This is defined below the table. Accordingly, the p-value is 0.000, which is less than 0.05. From the p-value index table, this means that we have sufficient evidence to reject the null hypothesis because the correlation coefficient differs significantly from 0. Therefore, there is a linear relationship between the sample 3 and sample 1. The correlation coefficient between sample 3 and sample 2 is minus 0.048 and is a negative value. Again, if you look at the index table, this coefficient falls between 0.0 and less than 0.10, and this indicates that there is no linear correlation between the two samples. Since the coefficient is negative and there is no linear relationship or linear correlation between the two variables, there will be nothing to talk about the negative sign, which is supposed to indicate the direction of the correlation. So the graph will be the type that projects from the y-axis and parallel to the x-axis. Accordingly, the p-value is 0.841, which is greater than 0.05. From the p-value index table, this means that we have no sufficient evidence to reject the null hypothesis because the correlation coefficient does not differ significantly from 0. Therefore, there is no linear correlation between the sample 3 and sample 2. Now, the correlation coefficient between sample 4 and sample 1 is minus 0.774 and is a negative value. Again, if you look at the index table, this coefficient falls between 0.70 and less than 1.0, and this indicates that there is a very strong linear correlation between the two samples. Since the coefficient is negative and there is a linear correlation between the variables, it means that as sample 4 increases up the scale, sample 1 simultaneously decreases down the scale. So the graph will be the type that projects from the y-axis down to the x-axis in a falling pattern. The double asterisk mark standing as superscript to the coefficient show that the correlation is significant even at 0.01. This is also defined below the table. Accordingly, the p-value is 0.000, which is less than 0.05. From the p-value index table, this means that we have sufficient evidence to reject the null hypothesis because the correlation coefficient differs significantly from 0. Therefore, there is a linear correlation between sample 4 and sample 1. Moving forward, the correlation coefficient between sample 4 and sample 2 is 0.119 and is a positive value. Again, if you look at the index table, this coefficient falls between 0.10 and less than 0.30, and this indicates that the linear correlation between the two samples is low. Since the coefficient is positive and there is a linear correlation between the variables, it means that as sample 4 increases up the scale, sample 2 simultaneously increases up the scale. But the increment in this case is low in both ways. So the graph will be the type that projects from the origin of the x and y axis. Accordingly, the p-value is 0.617, which is greater than 0.05. From the p-value index table, this means that we do not have sufficient evidence to reject the null hypothesis because the correlation coefficient does not differ significantly from 0. Therefore, there is no linear correlation between the sample 4 and sample 2. These findings look contradictory, but let me explain. As you can see, the p-value indication is obvious because the magnitude of the coefficient is small and not too far from 0.0. And by virtue of the index table, the correlation is defined as low. However, the p-value failed to see this value as sufficiently significantly different from 0. So because the correlation between the two variables is low, it is as good as saying there is no correlation. I hope you are able to understand this explanation. Finally, the correlation between sample 4 and sample 3. The correlation coefficient between sample 4 and sample 3 is minus 0.775 and is a negative value. Again, if you look at the index table, this coefficient falls between 0.70 and less than 1.0. And this indicates that there is a very strong linear correlation between the two sample variables. Since the coefficient is negative and there is a linear correlation between the variables, it means that as sample 4 increases up the scale, sample 3 simultaneously decreases down the scale. So the graph will be the type that projects from the y-axis down to the x-axis in a falling pattern. The double asterisk mark standing as superscript to the coefficient show that the correlation is significant even at 0.01. This is also defined below the table. Accordingly, the p-value is 0.000, which is less than 0.05. From the p-value index table, this means that we have sufficient evidence to reject the null hypothesis because the correlation coefficient differs significantly from 0. Therefore, there is a linear correlation between the sample 4 and sample 3. Please note that the 20 you see in this table that are assigned to n are the sample sizes or the number of cases used for the Pearson's correlation. Once again, as you can see, the numbers of cases are equal for each pair of correlation, and this indicates that there were no missing data or missing values in the data set. This is how to perform Pearson's correlation in SPSS, and I hope you will be able to replicate this procedure to analyze your own data and interpret the results. But right now, we have come to the end of this video. If you like this video and you want to see more video contents like this, please like this video by giving it a thumbs up, share this video, and subscribe to my YouTube channel to receive notification every time I publish new and useful content. Subscription is free. Thanks for your time and subscription. Thanks for liking the video, and I hope to see you again in my next video. Bye.